Okay, so today we start chemistry. And we talk about chemistry. Chemistry, or the more the physical science side of chemistry, basic chemistry and chemical properties, are talking about matter. Chemistry is the study of matter. So what is matter? Well, matter, it's hard to define. You kind of get into a circular argument of what is matter. Matter is anything that has mass. Oops, I don't know where the E came from there. Has mass and volume. In other words, it takes up space. Well, dark matter still takes up space and it still has mass. Dark matter, or what they're calling the quantum vacuum, is the new name they're using for dark matter now. Where that came from is they were looking at the universe and the expansion of the universe, and at one time they thought that only the planets and the stars and asteroids, the visible bodies, were the only thing that had mass, and it was a vacuum of empty space in between them. Like Earth has its atmosphere around it, but outside the atmosphere it's empty space. And what they found is even though it's not breathable, you could get out there and it would, it'd suck the life out of you. There's still something there because the amount of visible mass was not accounting for the forces of gravity and the bending of light, and also the expansion of the universe. The universe is expanded. The whole idea of the Big Bang, it started with a big explosion, it expanded really rapidly, and then it started to slow down because the gravity started sucking it back in. And it's still expanding, but the rate of expansion and the characteristics of that expansion were not accounted for by the visible mass. So they started to theorize that there must be mass in that dark space, the vacuum in between. That's where dark matter came from. It's not visible, but it has to be there because it has to account for the amount of mass that it needs to make all these other things make sense.
I heard it was kind of like a gimmick.
Yeah. Exactly. It's almost like an antimatter type thing. In fact, they just in the last few weeks they announced that they've developed a rocket, a thruster, that uses the quantum vacuum to create thrust. So basically, it's a free energy source. Yeah. If you look it up once, a quantum vacuum rocket, a quantum vacuum thruster. It should be out there. I know I saw posting about it on Facebook. And if it's on Facebook, it must be true.
In our lifetime, are we going to be interstellar?
Well, and that's what the hope is right now our biggest limit on any sort of long-term space exploration is fuel. Nuclear is our answer for long-term travel on Earth, but they can't make a nuclear thruster because to thrust a rocket it actually needs something that it can expel out the back. Our rockets right now use a liquid or solid oxygen and hydrogen combination. The only reason we use those is those are very, very compressible. So you can compress them down to a very, very small volume and then release it and it expands rapidly. When the rockets take off, that flame you see, it's not really a fire or explosion like you would think. All that is when that gas escapes and it's allowed to expand. It expands so fast that it heats up and it ignites. Normally when things expand really fast, they cool off, but because of the volatility of those fuels and the combination of hydrogen and oxygen, it's not an intentional ignition, it's just a side effect or a byproduct of it. Because it's a change of momentum. You release that gas really quickly in one direction, it causes the change of momentum, the rocket has to go forward. It's like standing in a boat in the middle of the lake and throwing something. The boat, even though what you threw goes that way a long ways, the boat actually moves backwards a little bit. It's that conservation of momentum. And so that's what's causing that rocket to lift off and move. It expels it. You have the booster rockets, because it takes an incredible amount of momentum to get it to lift off the ground and to escape gravity. But once it's in outer space, it doesn't take much. A canister the size of your gas grill, that canister could probably take you all the way around the world because you're very gravity free. There's not many forces acting on you. It doesn't take much thrust to get you moving. A fire extinguisher actually would probably give you a heck of a trip out there.
I saw a movie, Center
Oh yeah, there was one movie where they showed that. It's maybe not quite that.
Yeah.
You
Uh,
could just throw a wrench in the opposite direction.
And you would move, yes. Yeah, anything you threw in the opposite direction. Kind of like there's an old physics problem. If you are trapped at the center of a frictionless pond, a frictionless sheet of ice, how could you ever get off? Well, why don't you take off a shoe and throw it, or whatever, or take a leak, or spit, or whatever. And the change in momentum of one thing going one way causes you to. You may go very, very slowly because it's proportional. Let's say your shoe weighs, what, 1 pound, and you weigh 200 pounds. Well, you can throw that shoe 20 miles an hour that way. You're going to go 1/10 of a mile an hour that way because the ratio of weights will be the ratio of the velocities. But it is still a direct relation. It still will happen.
So the dark matter knows the
Well, they didn't really explain how the thruster worked completely, but it is accessing the transfer of the interaction between the dark matter, the anti-universe, and I kind of skimmed through it. I didn't read it in detail, and I'm not totally sure I'd understand it even if I did sit down and read it in detail. And I read it this weekend, which means there might have been some. Here we go. So anyway, mass is, and this, like I said, this is where the argument gets circular, because what is mass? The definition of mass is the amount of matter in an object. It's kind of, yeah, what is matter? Well, it's something that has mass. What is mass? It's the amount of matter. Yeah, okay. There's a very, very subtle difference between mass and weight. A lot of people mistake the two. In fact, we tend to use them interchangeably. They are not. Mass is the amount of matter. Weight is the force of gravity. Now, what's that? Exactly. Now, because we're on Earth and we tend not to leave Earth, and gravity tends to be pretty uniform throughout the whole Earth, we use them interchangeably, and that's probably okay. Now, gravity is not totally a constant on Earth. Because the Earth is slightly elliptical, like this. Think about it. You take a foam ball and you spin it. On the surface of the Earth is, what, 15,000 miles around the equator? It spins in 24 hours. That's moving pretty darn fast. I mean, that's like 800 miles per hour at the equator that's moving. That's flying along. So you take like a foam ball and you spin it, what happens? It tends to elongate. If you spin it fast enough, it elongates a little bit. That's what the Earth has done. Because of that spinning, it's elongated. So if here's the poles, it's a little bit wider across the equator than it would be from pole to pole. Gravity's slightly less here because it's, if you think of the mass as being concentrated at the center, it's slightly further away here than it is at the poles. Gravity at the poles is slightly stronger. But it goes from like 9.7 meters per second squared to 10.1 meters per second squared. So not a huge difference. They're talking like a 5% difference, max. So on Earth, we tend to use weight and matter interchangeably, or mass interchangeably. But technically, weight, as I said, is a measurement of the force of gravity. And the way weight is measured is by using a spring. Springs are used to measure force because springs have what we call a spring constant. It's a ratio. Double the force, you double the amount the spring stretches, unless you exceed an elastic limit of the spring. And so with the way weight is measured, you have a scale and you have this spring, and the weight, you put whatever you're measuring at the end of that spring and it stretches it out, and there's a little scale, an indicator there that shows how far that spring is stretched from where it started. And that's the weight, is the distance that spring is stretched. Mass, on the other hand, is compared to other known masses. So we use a balance. We have the object that we're measuring on one side, and on the other side we have our known masses. And we just stack them up until this thing balances. And once this thing balances, we add up what these known masses are, and that's the mass of this object that we were looking for. Derek said something about, well, mass doesn't change. If I go to the moon, where gravity is basically 1/6 that of what it is on Earth. You've seen the pictures of the guys in the little spacesuits, running in the moon, taking these huge steps. That's because gravity is very, very light there. They can take very huge. You can jump quite a bit higher on the moon as well.
Might be for the best.
Volume is
Yeah. No, mass does not change. Weight does. Weight changes. So think about that spring on the moon. If gravity was less, it's going to stretch a whole lot less because there's less force there. In fact, if it's 1/6 the gravity, it'd stretch 1/6 of the distance, so 1/6 of the weight. But on the moon, yeah, the force of pull on this object is going to change, but also it's going to change on the known masses. So it still takes the same amount of mass here to balance it out. So the mass cannot change by variations in gravity because, well, both sides are affected by gravity equally, whereas the weight will be affected. So weight is dependent on location. Mass is not. Mass is a property of the object. Weight is a property of the location of the object and the amount of mass that's within it. I mean, weight is proportional to the mass, but you must know what the forces acting upon it are. Volume, of course, is the amount of space that something takes up. So those are our main properties of physical items in chemistry. We talk about chemistry. There are some calculated items. The big one is density. Density is how tightly packed this matter is within the volume of an object. In fact, it is defined as mass divided by volume. So if I have an object that has a mass, and since we're dealing with science, generally we're talking about grams or kilograms, metric units, and let's say we have a mass of 200 grams and a volume of 50 centimeters cubed. Our density then becomes mass of 200 grams divided by 50 centimeters cubed. 200 divided by 50 is 4 grams per cubic centimeter. That's our density. There are two ways to change the mass. One, change the density. You can increase the amount of mass. If that amount of mass goes up to 300 grams, you can see now the density is 6 grams per cubic centimeter. Or you can change the volume. If the volume were to decrease, let's say this one here, we're going to decrease the volume now. We're going to have 200 grams still, but the volume goes down to 40 cubic centimeters. Well, the density now goes up to 5 grams per cubic centimeter because you have the same amount of matter, same amount of mass squeezed into a smaller space. And of course, with all the algebra we learned last semester, you can reverse that. Let's say you have something that is rated at 2.4 grams per cubic centimeter and has a volume of 20 cubic centimeters. To figure out what the mass of that is going to be, and this is actually probably the most used application of this. If you know what the mass of a material is, you want to know after you produce this, if the finished product is going to be a certain volume, how heavy or how massive it's going to be. Well, you have 2.4 grams per cubic centimeter is the density. That equals our mass over the volume of 20 centimeters cubed. And to solve for m, it's being divided by 20, so you're going to multiply by 20. Look familiar? So you get 48 grams. The cubic centimeters cancel out, so your mass is 48 grams. Good stuff, right? One thing you'll find, by the way, science, physical science, chemistry, is 95% math. That's why I get along with it so well. Next thing we want to talk about is the phases of matter. Now, most of us remember from our youth studying science that there are 3 main phases, or depending on who taught, 4 main phases of matter. Yes. Plasma is relatively new in the last 30 or 40 years that they've added that in. Plasma is actually what exists inside the sun, and it's inside most stars. Starting out, of course, we have the solid phase. Solid is usually at the coolest, lowest temperature. Most people believe that temperature is the only thing that affects the phases of matter. It does not. The other thing that affects it is temperature, but also pressure affects the phases. You can actually force water to evaporate, even though water evaporates or boils at 212 degrees Fahrenheit. At 100 degrees Fahrenheit, you can force it to evaporate by lowering the pressure low enough. It'll actually start to boil. In fact, I don't think I have it here.
One time, we had this like glass thing and they vacuumed all the air out of
Yep.
it. You could like hold it in your hand.
Yeah, I have one of those at home. It's a little glass thing that the air has been sucked out of it, and you hold it in your hand. It's actually rubbing alcohol that's in it. Rubbing alcohol has a lower boiling point than water, and that's how they keep it, in that. So, otherwise, if you sucked enough air out that water would boil in your hand, it would actually crush the glass. You'd have to have very thick glass. But yeah, rubbing alcohol boils at a much lower temperature than water does anyway. So you put it in there and you suck a majority of the air out of it. Yeah, you can hold it in your hand and it boils. I have one somewhere, but I don't think it's at school. Let me just. So we're talking about the phases of matter. I don't have my little hand boiler, but so you have the solid. But next, after solid, as you add heat, what would be the next phase? Liquid. Next is gas, and then finally plasma. Well, what a gas is, a plasma exists on the order of about 1,000,000 degrees. It's really hot, yeah. In fact, use Celsius, which is even hotter. Everybody thinks of a plasma as being a liquid. It's not. What it is it heats. Once you get so hot, or so it can also be just incredibly high pressure that forces the plasma as well. It becomes like it's still gaseous, but it's like electrically charged, and it's really weird. I mean, it's not a liquid. You couldn't even tell what it feels like because obviously at that temperature you try to touch it and your fingers are gone. It's just a very electrically charged, weird state. It's almost like being inside a storm cloud, little sparks bouncing around. I mean, at extreme amount of pressure. The way the sun creates a plasma, the sun is so huge, and it's all hydrogen. Well, it's mostly hydrogen. What happens is there's so much hydrogen that the gravity of the hydrogen itself pulling on itself into the sun, because there's so much of it, it creates enough pressure that it starts to squeeze the hydrogen atoms together, and it creates fusion, which causes it to turn into a plasma. So it has to be enough pressure to force the atoms to actually start fusing together. So I mean, we're talking extreme pressure. That's how much material. I mean, hydrogen is the lightest element known to man, and there's enough of it in the sun to cause enough gravity. And remember, the amount of gravity is based on the amount of mass. So it takes mass to create gravity. There's enough of it there to cause that much gravity to fuse those hydrogen atoms together and create a plasma. Now what's happening is, as the hydrogen atoms fuse together, they're not hydrogen anymore. They become helium. So our sun is slowly converting itself from hydrogen to helium. And in several thousand years, or hundreds of thousands of years, whatever, it will be completely converted over to helium, and that's when it goes nova. It'll expand and collapse back into itself. And there's a chance, if there's enough helium, the helium can actually squeeze itself down. The gravity of the helium can squeeze it down, start fusing the helium, and it can keep going. Helium would go into 4, would be carbon. And just keep going from there. Actually, no, 4. What's element 4? Carbon's not 4. Carbon is a plus or minus 4. Nope, oxygen is. Number 4 is beryllium. So it'd become beryllium first. And then number 8. Yeah. So it goes from 1 to 2 to 4 to 8 to 16. I mean, I don't think we've ever discovered one that's a 16, because 16 would be sulfur, I believe, if I'm remembering right. Yeah, 16 would be sulfur. Even 8 would be oxygen. I don't know if we've even discovered oxygen stars. So anyway, those are the 4 main phases. There are sub-phases in matter that we'll talk about in just a little bit. But what happens, let's start out with a solid. Let's say this is temperature here. Heat gets added to it. And then over here, actually, we call this temperature. And I think, well, aren't heat and temperature the same thing? Not really. If we add heat energy to something that is a solid, eventually there'll get to be a point where we keep adding heat, but the temperature does not increase. What's going on there? It's turning from a solid into a liquid. The energy from the heat is no longer increasing the temperature. The energy from the heat is going to break the bonds between the atoms to change it from a solid into a liquid. And it becomes a liquid. Now, most people think that a substance gains heat, converts heat into temperature at the same rate regardless. It doesn't. Once it goes from a solid to a liquid, it might take more heat or less heat to change its temperature. Its thermal properties change, like water. Water is actually very slow to absorb heat. Ice, on the other hand, is an extremely different case compared to the water itself. Very different thermal properties from one phase to another. So anyways, a liquid, you add heat, eventually at a certain point, you keep adding heat and the temperature just stops going up. What's happening? It changes. It's using that to break the bonds even further to change it from a liquid to a gas. We'll talk about the molecular bonds within these, how they change from one phase to another more on Wednesday. For right now, that's enough is to look at it like that. In a solid, there are two main types of solid I want to describe. Most of what we're used to is what you call crystalline solid. Metals, most really hard, rigid solids, like the surface of these tables, those are crystalline solids. The molecules, the atoms are arranged in a definite pattern, in a definite order, and they're bonded really tightly together. So what we call it, if you were in a material science, they'd call it long-range order. And it's basically just an organized little, links like this where they're hooked together. And very rigid, very hard. This is the whole theory of metallurgy, which is changing the strength and hardness and stuff of metals, is based around that, of altering that crystalline form, that crystalline structure to change its properties, making it stronger, making it more softer, more malleable, making the surface harder. Strength and hardness do not always necessarily go together. And then there is something called an amorphous solid. Jello, yeah, amorphous means it does not have that crystalline structure. And in the amorphous solid, tar would be a good one. It's a solid. A lot of people think it's a liquid. It's not. It's a solid. It's just a very flexible, malleable solid. Wax is another example. It's a solid, but you can form it. Well, the human body is quite different. The human body, that's a question I've never had. Is a living tissue amorphous or? I might have to do some research on that one. I've never actually had that question come up before. I would say it's amorphous. We don't necessarily have. We really can't have a crystalline structure. Yeah. Well, our bones though might. Our bones probably do have a crystalline structure.
With the crystalline structure, there's still volume between them.
Well, and that's one of the things that can be done to strengthen it. Like so you've got these atoms here that are like this big, right? And they're still stuck. There's still going to be gaps in between them just because of the way they're stacked. If you put ping pong balls in a pail, there's going to be air gaps between them. Well, you can see that you can actually fit a smaller atom in there and it would actually fit right in the hole. It wouldn't increase the volume or anything. So you can increase the density by inserting those smaller atoms. That's, metallurgy and alloys do that. But they found that if you take an atom that's slightly too big to fit in that hole and stick it in there, what happens is it stretches the solid. So you have this pattern that normally looks like this. If my drawings were not so crappy. And now you've stuck that atom in there that stretches it out. So now it looks like this. It's stretched out around that one atom that's stuck in there. And now being stretched, these rows of atoms that were in nice, neat little rows before, now are not in nice, neat little rows. Now they're bowed out a little bit like that because that extra atom in there. Well, here you think about it, if you go to deform this, they're nice, neat little rows. They can slide nice, neat little rows. They just have to kind of like go over the bump, like if you put your knuckles together, they just kind of go over that little bump of the knuckles. Same there. But now this is bent. Now it not only has to slide nice, neat little rows, it has to slide around that little bend in it because there's that extra atom in there. It's like putting sand in a bearing of a car wheel. It grinds in it and it slows it down. It's the same type of thing. It increases the friction between. They're called slip planes. And by adjusting that crystalline structure now so it's not so perfect, it's kind of a paradox. Imperfections in the crystalline structure make it stronger to an extent, until you get too many imperfections in it that it starts to fall apart and gets weak. Another way to do it is just you pull one of those atoms out completely, and the other one starts to collapse back in to fill the hole, and that changes the structure too and makes it stronger. Well, it's a matter of, there's a process, is like you bend something called cold working. You bend something, so you've got this definite, rigid structure. Now you take it and you bend it. Well, it's going to cause, these are going to pry apart, and since they can't stretch, they pry apart and they create gaps in between them, or atoms fall into the places or whatever. I mean, there's things they can do by doing, just physical things to it. Work hardening is exactly it. They don't know exactly how much is going to happen, but they know some is going to happen. The whole theory of heat treating, it goes off these phases. We said that there's solid, liquid, and gas, but within the solid, there are subphases, and it has to do with those only crystalline solids have subphases in the solid state. What happens is actually there's small subphases in here, like iron has two subphases, delta and alpha. In one subphase, it's structured like this. Its crystalline structure looks something like that. In fact, that's warmer. It starts out structured like this, with the atoms stacked directly on top of each other. As you heat it up at a certain temperature, you hit a transformation temperature, and the crystalline structure changes to this one, where the rows are staggered. It's more compact, more dense, more strong. But if you let it slowly cool down, when it hits that transformation temperature again, it's going to change over to this. So the whole theory of heat treating is you heat it up above that temperature, get it up somewhere in here, then you drop it in cold water or oil or something, you quench it really fast. Some of it's going to change back to this form, but some of it's going to be trapped. It's cooling so fast that the atoms can't move, and now it's stuck in a more dense, stronger state. That's what heat treating is. Problem is, as it gets stronger, it also gets more brittle. So you got to worry about that too, that balance between strength and brittleness. But yeah, there's a lot. I could go on for hours about the subphases too and all that, and I won't.
So the old blacksmiths, did they even know?
They didn't really know.
If I hit this with a hammer and heat it up and cool it out.
Well, not only that, but most of them were using charcoal or coal itself for heating it. And charcoal and both coal have a high carbon in them. And what was going on there, not only was it the heat and then quenching it, and they actually learned some things, if they quenched it in water too fast, like a hammerhead, they made a hammerhead and quenched it in water too fast, they'd go to use it and it would crack because it would be too brittle. So they learned that you had to let it sit there for a couple minutes and cool, and they just went by the color. Again, messing around until they found something that worked, that when it went from white to orange, then they could stick it in the water and quench it. It'd still be hard, but it wouldn't crack when they used it. And so they went all off of the color of it. But the carbon in the charcoal and the coal that they used, well, as they stuck it right in there to heat up. Well, some of that carbon coming out of there absorbed into the surface of the metal, and it's called carburizing. Now they actually put it in a heat treat oven. They have a canister of carbon gas there. They turn it on and they force the gas into it as they heat it up, and it penetrates the surface and it carburizes the surface. They found adding carbon. Well, I mean, steel is iron combined with carbon. Higher the carbon, the higher the strength. Problem is, if you alloy the carbon into the steel, the whole thing is strong, but it's very brittle. If you leave it as mild steel on the inside, low carbon, then you just infiltrate the very surface of it with high carbon. You get on the inside, it's soft and flexible enough that it doesn't crack, but you got a very hard surface. So you can use the hard surface now for different uses. I mean, yeah, there's a lot of the old blacksmith is a great example of just basically dumb luck and experience. He had no idea why it was working. He just knew that every time he did that, it worked out. Okay.